Welcome to the lecture about the simple linear regression model. And we'll get started here with an example of a response variable that is called interval and a x variable, a predictor variable called duration. And these data are from Old Faithful Geyser in Yellowstone National Park, where duration measures the number of seconds that the eruption for Old Faithful has occurred, the previous eruption. So 200 would mean the previous eruption was 200 seconds long. And interval measures the number of minutes that it takes for the next eruption to occur if the last eruption was, say, 200 or 250 seconds. And what you observe from this plot is that as the previous eruption is longer and takes longer to occur, or lasts a longer duration, it takes longer waiting time for the next eruption to occur. You can see a basic upward pattern. The longer that a previous eruption was, the longer you have to wait till the next one. And this is an example of a basic situation with one predictor variable and one response variable. This plot was constructed with the code that's given here over on the left. We use the Old Faith data frame that is in the ALR 4 library textbook package for our course, and we plot the y variable interval as a function of duration. And then what we do in the third command is estimate a linear model, which basically tells us what equation of a straight line goes through these points the best. And this LM function produces an object called OF mod, or Old Faithful model. And then what we do in the fourth command is we plot and superimpose the very best straight line that we can through these points. And that's how we made our display in R. And that brings us to the simple linear regression model, which might be a way to describe such a data situation that we were looking at here for the Old Faithful Geyser data. It looks like when we look at these data that the relationship between duration and interval might reasonably be described by a straight line mean function. And so the simple linear regression model says that a y observation, yi for the ith observation on the y variable, might be supposed to be generated by this kind of mechanism where there is an intercept beta naught plus a slope beta 1 times the predictor value xi, and then plus or minus some random error e sub I, and that is a data creation mechanism that might be responsible for points appearing the way they do in this data display. So the issue is not how are these points and what are these points doing on this particular display, but rather a larger issue of how did these points get here? What was the data creation process that made them? And there's a famous old saying that all statistical models are wrong, but some are useful. And here's a case where the simple linear regression model is a very useful summary and explanation for how data arrive in our data analysis system. No data creation system is probably exactly a straight line, but often they're close enough to being a straight line pattern that this representation is useful. So what we're saying up here at the top mathematically is that the y value is related to a mean function and then some random error around that mean function, and the mean function is an equation of a straight line. Here is the thing that controls the intercept of the data creation mean function. The beta 1 parameter controls the rate of change, or the slope, between y and x in the data creation system. Beta 0 and beta 1 are unknown values. We believe they exist, and our job as statisticians is going to be to measure and estimate them the best we can and try to understand how the data creation system works. But we are not going to typically know what these values are, and these things are called beta 0 and beta 1 are called parameters. The final part of this simple linear regression model concerns these random errors, the E sub i's. These things are basically operating according to a variance function that is a constant. No matter what the value of x is, the variation in y is a constant sigma squared. So what we're saying here on the last part of the simple linear regression model is that the variation around the mean function, how much y values vary above and below the mean function, is controlled by a quantity, an unknown parameter, sigma, and that this is what controls the variation. Here is a picture showing the underlying data creation mean function with an intercept beta 0. That's basically the value of y that occurs when x is 0. And beta 1 controls the slope, or the tilt, of the underlying mean function that is generating the data. Here's another display that tries to illustrate what we mean with the simple linear regression model. This line underneath here is representing the straight line mean function, and then at a particular value of x, like here at 45, we imagine that there is random variation in the process that produces the y values, basically the E sub i's. And the E sub i's might be giving you a little bit of a value of y that's above the mean function value, or maybe a little bit below the mean function value. But this diagram demonstrates with these bell-shaped curves the idea that the y values are generated randomly above and below this mean function according to how much this random variable E sub I might be. It's a random process and a random value. The simple linear regression model has some assumptions. The first assumption is that these random errors that we've been talking about, the E sub i's, on average they're 0. And that's represented by the idea that on average data values might be randomly drawn above the mean function or below the mean function, but on average these innovations are, on average, they're 0. Sometimes we get data values that are above the mean function, sometimes we get them below, but on average these random things have a mean of 0. The second assumption we've talked about, that the variation of these randomness and error process is basically the same. There's the same amount of variation no matter where you are on the mean function. What we'd be saying here is at an x value of 45, the spread of y around the mean function is basically the same as it is down here at 25 for x or any other value of x. The third assumption is that our errors are independent. In other words, that the error random variable for the ith observation is statistically independent from the error observation for the jth observation. The final assumption is that the errors have a normal distribution. And this is not terribly crucial in practice and is really only relevant for talking about the production of confidence intervals and hypothesis tests when we have small samples. When we have large samples, this is really not an issue at all. So to review, we have a simple linear regression model that tries to help us understand how a scatter plot like the Old Faithful geyser can appear the way it does. Basically what we say is that underneath this scatter of points there was some underlying straight line that exists, and then there is random variation above and below that straight line that makes these points arrive the way they do. Our job as statisticians is to try to figure out what that underlying data creation straight line is like. The one that's here on this plot is a data estimate for what we believe the underlying creation system to be. And we're going to be talking more about that in this presentation. After the model assumptions, let's take a look at how to get an estimate of this underlying straight line mean function. The way we do it is called least squares estimation, and it's based on the idea of a residual. Hopefully you've seen or heard of residuals before in a previous class, but I'll remind you that it's just the distance between an actual observed value, a y value of a point on the scatter plot, and an estimated value on a straight line, and that is represented statistically, notationally by yi hat. And so yi hat means an estimated value for a particular observation y. And what we do is to try to estimate the slope and the intercept that will put a straight line through the points the best it can to minimize the sum of the squared residuals. And so right down here in this third bullet we can see that we have summation, and inside the parentheses is a residual for the ith data value, and then we square it. And so the objective is to produce a value of residual sum of squares that is as small as possible. We find the slope and we find the intercept that produces the smallest residual sums of squares that we can. And conceptually that is done by adjusting the slope and the intercept of the underlying line so that it goes through the points on our scatter plot in such a way that these little vertical distances or residuals are as small as we can make them. And so we adjust the line until we find exactly the right slope and exactly the right intercept that makes a line going through these points the best we can, so that these distances between actual data points and an estimated line are as small as possible. On this diagram, the distances between the points and the line are residuals. So this point here would represent a value of y that's a little bit above 3. The point right here on the line would be y hat, and the distance between y and y hat in this case would be a slightly positive residual. A case like this one right here, where the value of y is smaller than y hat, you would have a negative residual. Here are the numerical formula equations for the very best slope, beta 1 hat, and the very best intercept, beta naught hat, that will produce the equation of the line that goes through our data points the best that they can. So when we ask R to compute an estimated straight line for a scatter plot, like for the Old Faithful data, R is using these formulas in its computations to produce the very best slope and the line with the very best intercept. Sxy over Sxx is the formula for the best slope, and I have the value for Sxy given right down here. It's just a sum of y deviations for the values around the average value of the response variable. multiplied by the deviation of the predictor variable around its average for each data case added up with this sum, and SXX is just the sum of the squared predictor values around its average, quantity squared, sum of squared differences. The estimate of the variation, so remember sigma represents in the underlying data creation system the variation of the data values around the mean function, or in other words the variation in the E sub i's, the random variables E sub I. Well, we can estimate that variation by using the residuals, and we notice we do that right here inside the square root. We take the sum of the squared residuals, we divide by almost the number of data values. This is almost like dividing by n, so that we have an average squared residual, and then we take the square root and we get something like an average residual. And so that is a good estimate of how much variation is in our data creation system. To do statistical work, we need to understand how these estimates will operate in order to gather proper meaning and make proper inference. One of the things that we want to know is that when we use these estimates, the ones I've been talking about right here, beta 1 hat, beta naught hat. Oh, by the way, whenever statistically we have things with hats on them, those mean estimate of. So beta 1 hat means estimate of the underlying data creation parameter beta 1. Beta 1 we're never going to know the value of. We're never going to exactly know how the data were created exactly, but we can estimate it from the actual observed data that came from the system, and that produces the estimate beta 1 hat. What we're going to want to know is that if we make estimates over and over with this kind of a formula, how do they behave? On average, what do we get for beta 1 hat? What's the average value that we will have? How much variation will the estimates have? And in the third bullet, we point out that an estimate of this variation is called a standard error. And typically what we do is we have a formula or a derivation for what the variance or the standard deviation is in our estimate system, in our estimate formula, and then what we do is we plug in an estimate of the variation parameter sigma, the sigma hat value that we just talked about right here, and we plug that estimate in for wherever we would ordinarily need to have an actual value of sigma, and that produces estimated variations, which are called standard errors. We'll see those formulas in a moment. The first statistic or parameter estimate we're going to study is that for the estimated slope. So there is a estimation system right here for producing a guess as to what the right underlying slope might be that created these data, and this formula defines it. And what this overhead shows us is that on average, capital E means expected value, on average this random thing tends to be the real value of the parameter. And that's a very reassuring statistical thing, that this estimation routine on average gives us estimated slopes that are the real slope in the data creation system. And it doesn't say that every estimated slope is going to be perfect. It's just saying that if we repeatedly use least squares estimates, sometimes our beta 1 hat will be bigger than the truth, and sometimes beta 1 hat will be smaller than the truth, but on average these estimates for samples of size n, on average they will be the right value, and that's a very reassuring thing. The formula for the standard deviation, the square root of the variance for this estimate, is given by sigma over the square root of SXX. The thing you got to realize is that when you create a new random sample of n points from the data creation system, the simple linear regression model, beta 1 hat will be different in one sample than it is from the next random sample. They'll probably be similar, but they will vary, and this expression tells you how much they will vary from sample to sample. And it's really controlled by just a few things. One of the things that's involved is the variation in the data creation system. How far do points drift above and below the real underlying mean function? When that variation in the system is bigger, the variation in our slope estimates is bigger. That makes sense. Another thing you'll see involved in this variation formula is the quantity SXX. And I'll remind you back from a previous overhead, SXX is how much variation the predictor values have in the scatter plot. How much spread is there around their X bar? And so what you can see is that if that is bigger, the denominator is bigger. And that means the fraction is smaller. So more variation in the predictor values gives you a smaller variation of the slope estimates, or in other words, a better, more precise estimate of slope. The other thing that's involved in SXX, if you look at the formula, is that you're summing over the number of data values. It's not given here explicitly in this subscript, but this is a sum going from 1 up to n. And so if you have more data, you'll have more squared differences being contributing, and SXX will get bigger, which will also again make this fraction smaller. So in other words, more data you have is going to decrease the variation and the uncertainty that you have in your slope estimate. I think that makes sense. Here is a demonstration about what I've been talking about here. I've set up a data creation system on a computer where the real underlying slope rate of change is a value of 0.03. And I created data sets and scatter plots. And from each scatter plot that I created, I made an estimated slope. And I used R to come up with a guess for what the right slope should be from that scatter plot. When I have only 50 data values, you'll notice a very interesting bell-shaped pattern for my estimated slopes. You'll notice that they tend to gather around the truth. That is not surprising. That is what I said would happen right here. That is what it means that on average, estimated slopes from different random samples will on average equal the truth. And you'll notice you see that right here. Remember, the truth is 0.03, and notice that my beta hats tend to average around 0.03. Some random samples gave a slope scatter plot, a scatter plot of points where the slope was a little bit bigger than the truth in the data creation system, and some scatter plots gave me an estimated slope that was less than 0.03, but on average they're 0.03. The same is true over here when my data set is 500 observations, so the scatter plot has more points on it. You'll notice that for the scatter plots that have more points, the estimated beta 1 hats, notice they tend to hang around 0.03 just like they did for smaller samples. But notice the variation in the estimated slopes is so much notably less than it is for the smaller sample size. And that happens because of this expression. SXX down here is a much bigger value when the data sample size n is 500 than when it's 50. And so when you have more data, it makes the standard deviation smaller, and we see that carried out right here in this simulation. This is what we were talking about on the previous two overheads about the variation in the estimates. The same thing can be argued for the estimated intercept. On average, our scatter plot least squares best guesses for the intercept will on average be the true intercept. And here is the expression for how uncertain the beta naught, the intercept estimates will be from sample to sample. And you'll notice there's some of the same things in here. If the data creation system variation sigma is bigger, the variation in our estimates is bigger. When there's more data and n is larger and SXX is larger, the whole variation in the estimate is smaller. And so this gives you an idea about what controls the variation in estimating the intercept. Final property is about how estimates of the slope and the estimates of the intercept vary together, the covariance, which is going to be related to correlation, not exactly correlation, but it does control the relationship between the two estimates. The important thing about this overhead is the fact that there is a negative sign. -1 times a positive number times x bar times another positive value SXX. And what this suggests is that when the slope estimate is bigger, it tends to mean the intercept estimate is smaller, a negative covariance or a negative correlation. And you might be able to understand that by thinking about a line like, like this one. If you've got a data scatter plot that has a steeper tilt than this one, notice the beta 1 value or the beta 1 hat would be bigger, steeper slope. Notice what will happen to the intercept. It will cut the y-axis at a smaller value. And that's, I think, the intuition behind why the estimated slope and the estimated intercept are negatively related. When we take a look at our formulas for the variation of these estimates, they have sigma values in them. And we never really know what the underlying data creation system variation is. The best we can do is use the residuals to come up with a guess or an estimate for what the error variation value might be. And we use sigma hat wherever we saw sigma in these previous formulas, like back here on overhead 15. This is how much variation beta 1 hats will have. Well, if we want to get a guess for how big that might be in a data set, using our data set to speculate, put in the data set estimate for sigma hat, and you will get expressions for standard errors. So these would be standard errors. These things we can compute from an observed data set or a scatter plot. The real underlying true variances are unknown because they involve things that are unknown parameters that we just don't know the values for. Here's how you might carry out least squares estimation in a real data set, like for the Old Faithful data set. We invoke the ALR4 package library. We get the data for Old Faith. We estimate the Old Faithful model using the LM function, interval being the y variable, duration being the x variable, and we get a set of estimates that we can ask R to tell us about what beta naught hat and beta 1 hat might be, and we get a summary of this regression model object OF mod, and it gives us several things we've talked about. It gives us a column of estimates. These are going to be the beta hats, and it gives us a column of standard errors, and we've just talked about these SEs or standard errors. So where it says intercept, that is going to mean that the estimated intercept beta naught hat is 33.987 minutes, and the estimated slope is 0.1769, and that is beta 1 hat, and the standard errors are given right next to them here. And so the way we would interpret things like this, the estimated intercept says, well, how long would we expect to wait for the next eruption if the previous eruption was 0 seconds long, or that it wasn't very long at all? Well, this would say that we should expect to wait about 34 minutes no matter what the last eruption might be. The slope, remember, is how much additional value or change in y you will have for a 1 unit increase in the value of x. And remember, the value of x is seconds of eruption. So for an additional second that the geyser erupted, you should expect to wait about 0.177 seconds. 0.177 minutes, which is about 11 more seconds. So for each second longer the previous eruption was, you should expect to have to wait an additional 11 seconds or so for the next eruption to occur. Well, you've learned how to estimate these parameters using R and using the data, and now we need to know some things about how to do statistical work, like making confidence intervals and making tests. And so we'll use the amount of uncertainty that we can measure in our data to come up with methods to tell us about the underlying data creation system. We're going to be using confidence intervals and tests, and here's a case where when the random errors EI have a distribution that is normal, the confidence intervals and tests can quite easily and correctly be based on the student t-distribution. However, statistical researchers have found that when you have a lot of data, the assumption about normality of the errors is not terribly crucial, and that the t-distribution methods that I'm going to show you here are appropriate even if the error distribution is not terribly normal distributed and not close to being normal. The methods still work if you have quite a lot of data. The formula for a confidence interval about one of the beta parameters, like beta naught or beta 1, is to just use the estimate, beta hat, plus or minus a t multiplier from the t distribution with the appropriate degrees of freedom, times the standard error that we get from our output. The degrees of freedom in this case for the t distribution is n minus 2. The reason it's n minus 2 is because there are n observations in the data set, and there are 2 parameters being estimated in the least squares system, beta naught and beta 1. A hypothesis test would be done using a t-statistic with the beta hat estimate minus whatever value you want to examine in the null hypothesis, here called value, would be a number. It's quite frequently a value of 0. You're often going to be interested in whether a beta parameter, particularly the slope parameter, is a value of 0. Not always, but frequently is a value of 0. And then you divide by the standard error of that estimate. And that produces a t-statistic that you can use for hypothesis tests. Creating confidence intervals for the beta parameters is really quite easy. In R, you just use a confint command, and the argument of the confint command is just an estimated regression model that you would have created earlier, like right here, OF mod. You estimate ordinary least squares to estimate the simple linear regression model, and you use that object in the confint command. You tell it what confidence level you want, and we get confidence boundaries for the slope under the duration line, and we get a confidence interval for beta naught, the intercept parameter, here under the intercept row. So what do we see here? Well, there is very, very clear evidence that the real value of beta 1, the true underlying slope parameter that created our scatter plot, is probably something that is a positive number, because the entire confidence interval boundary for the beta 1 parameter is positive, and it suggests very clear evidence that the longer the previous eruption was, the longer you're going to have to wait for the next one. In this overhead, I go through the gory details about how to use the confidence interval formula to get the confidence interval. Basically what I'm doing here is I'm taking the second estimate from the model, the estimated slope, beta 1 hat, and I'm subtracting off the correct t multiplier to get a 95% confidence interval. Remember, you'd use the 975 percentile to make a 95% upper boundary, and then here is the square root of the variation to get the standard error. And notice I get the same lower boundary as I did in the confint command, and here is the same upper boundary in the confint command. You would never do this, but I just want to show you that the confint command that I'm talking about right down here really is using the formula that I pointed out here on overhead 24. To do a hypothesis test, probably the most commonly done hypothesis test is the one about the slope parameter being 0 against an alternative hypothesis that's not 0. We would plug in beta naught, we'd plug in beta 1 hat right here. We'd subtract off the value that we're hypothesizing for the slope parameter, value of 0, divide by the standard error for the slope parameter, and we get a t-statistic of 33.05. We would use the t-distribution to calculate the p-value. What's the probability we could get a t-statistic more extreme than 33.05? That would just be the probability of getting a t-statistic bigger than 33.05 plus the probability that we could get a t-statistic more negative than negative 33.05. And because both of those tails are the same, I'm just going to look up one of them and multiply by 2. We find out that that probability is extremely, extremely small, and we get the following conclusion. Please pay close attention to these conclusions, because these are how I'm going to want you to do your conclusions on your exams and on your homework and quizzes. The small p-value means that the data are inconsistent with the null hypothesis, and that means there's evidence to doubt the null hypothesis, and there's evidence to support the alternative, that there is a relationship between the waiting time and the previous eruption duration, and that means there is evidence that the underlying slope parameter value is not 0. Remember that that alternative hypothesis was that beta 1 is not 0. So there's evidence that that underlying parameter is not 0, and because the estimated slope, the beta 1 hat, was a positive number, we've got evidence that the waiting time increases as the previous eruption took longer. And so that would complete a hypothesis test. I'd like to point out that this hypothesis test for the slope is carried out right here on our output. When we look at the row of the estimates table, remember this is beta 1 hat, this is the standard error for beta 1 hat. Here is that t-statistic, 33.05, that we saw from dividing this estimate by this standard error. And notice the extremely small p-value that we get right in here. So the hypothesis test for each parameter, either the slope or the intercept, being different than 0, is carried out for your convenience right in the estimates table. So keep that in mind. You don't have to go and construct that test by hand. It's given automatically. Our next topic is about using the information we have about y and x to make a prediction about what y will be based on a previous value of x, denoted here by little x star. So there's two possibilities here. One thing is we might be interested in learning and predicting something about the mean function. What do we think the average value of y is going to be at a particular value x star? Another possibility, in the second bullet, might be that we really don't care exactly about what the mean value of y will be, but rather what's an actual value of y going to be when the value of the predictor is going to be x star. What I want you to realize is that if the simple linear regression model holds, if you plug in a value of x star into the data creation system, you'll have a random draw of variation that will produce random variation in the scatter plot, and you'll get a value of y star. So this means that even if you somehow knew the beta naught and beta 1 parameters exactly, you still wouldn't be able to totally know what the value of y star is going to be because of the random variation e star. In this last bullet, we point out that our point estimate for what y is going to be is y tilde or y wiggle star, and that's found by just plugging in the value of x star into the least squares summary equation. And we're going to have to figure out what the right amount of variation is to come up with appropriate confidence statements about this prediction. So if we're interested in trying to understand the average value of y when x is x star, well, we just plug in, we plug in the value of x star into our estimated equation, and on average, the estimate that we would get is the real mean function evaluated at x star. So this says, on average, what will this estimate be? Well, on average, it'll be the real mean function in the data creation system evaluated at x star. The variation of this estimate is given by this formula. And so what you can see from this is, well, what matters to the estimate and the variation? Well, more variation in the data point creation system makes more variation in our guesses. Having more data makes n bigger and sxx bigger, and so that makes the whole variation smaller. That makes sense. More information reduces our uncertainty about what the mean function is like. The interesting thing that's going on here is that as you ask questions away from the center of the x predictor values, the variation of your prediction or your inference become more and more uncertain. As you move away from where you have a lot of data, your variation increases. Here is how you would be able to use R to, for example, try to learn about what the value of the mean function is, how long you have to wait in minutes for a previous eruption duration that was 150 seconds. Notice what you do is you use a predict command, you put in the R regression model object, OF mod. You provide a new value of the predictor variable duration in a little mini data frame data set that only has the duration of 150 seconds. You ask for the option interval to be confidence so that you make your statements about the mean function, and then level 95 means 95% confidence interval. Your estimated mean function is about 60.5 minutes, 60 and a half minutes, with a lower bound of uncertainty of about 59 and a half minutes and an upper bound of uncertainty about 61 minutes. So there is very, very precise information in this data set about what the mean function is going to be. It looks like you're going to be typically waiting about 60 minutes or so. Maybe as little as 59 and as high as about 61 or 62 minutes. This is a confidence interval about what the mean function is doing. This is not a statement about what a particular waiting time for the geyser would be, because that's the next thing about what an actual value of waiting time would be. We'll work more on that distinction after we talk about the actual value of y. So if we're interested in predicting y when the predictor is x star, we observe that on average our estimates are going to be the mean function evaluated at x star. And that sort of makes sense that on average that'll be the value. Notice, however, that the variation in what a y observation might be is a very similar formula to what we had when we're trying to estimate the mean function, except for an additional term of 1 inside the square root. And that basically, when you factor inside the quantity sigma coming inside sigma squared, that's the extra bit of uncertainty from the fact that even if you know the beta parameters that was back here, that even if you know the beta parameters, there's a sigma squared of uncertainty from the random error component. And so this variation is always going to be somewhat bigger than it is for estimating the mean function. And this would be the appropriate amount of variation to use if you're trying to figure out what should I expect from a single value of y when the predictor is x star. You'll request this kind of a confidence interval in R from the same kind of predict command and the same duration of 150 seconds. The difference is this option interval equals prediction. This is how you specify that I want a range for what an actual value of y is probably going to be. So in this case, what you can see is that our best guess for the waiting time is about 60.5 minutes. But our uncertainty and our range ranges from about 48 minutes up to about 72 minutes. This is the right range for an individual geyser eruption waiting time. This is not a statement about what the typical or the average waiting time is and how uncertain the average is. This is how much variation there would be in single instances when you got your family at Old Faithful Geyser and you want to know how long you're going to have to wait. Well, it's quite an uncertain range of somewhere under an hour to way over an hour that you would have to wait. So notice that this range is substantially bigger than what it was for trying to estimate the mean function. This is probably the one that is relevant for this application. You want to know how long you're going to have to wait for the geyser in a particular visit to Old Faithful. In this picture, you can sort of see the difference. The solid lines, here's 250 second previous eruption. The solid lines give you the level of uncertainty for how long you'd have to wait for an individual eruption. This would be the confidence bounds for individual values of y. The narrow dashed lines is how uncertain we are about what the mean function would be. So we can be quite certain and know the mean function very well, like we do in this case, but individual eruptions are going to have variation that just cannot be controlled by having more data estimating the mean function. We already know the mean function almost perfectly. The variation we have left over is just the natural geyser to geyser eruption variation that is not really a statistical problem. It's just the way the data system is. The next thing we're going to talk about is R squared, and that involves understanding a partitioning of variation. On the left we have an actual value of y and how far it is from its average. And you can break that distance up into the distance between the actual value of y and the estimated value on the line. In other words, this is like a residual, plus the distance from the line to the overall average. And we call this first part of the variation the residual variation, RSS, and we call this variation the variation due to the regression or due to the model, SS-reg. And from these parts of variation you can make a quantity called R squared. And it's just the variation due to the model divided by the total variation. And the way we would interpret this is that it's the fraction of total variation in the response that's explained by the regression model or the predictor. And you can get this value from our output by using the summary command. Summary of a regression model object gives you all of this information, and near the bottom you'll see multiple R squared, 0.803. This is the value of R squared for the Old Faithful waiting time problem. What does it mean? Well, this is a fraction of variation in the waiting times that can be explained by knowing how long the last eruption was. And so I'm looking for you to use this second bullet in your answers on quizzes and homeworks. It means that 80.3% of the variation in the waiting times can be explained by the values of the last eruption duration. This second bullet is how I'm looking for you to explain R squared. R squared is a value that can go from 0 to 1, 0% to 100%. 100% would mean that the predictor is a perfect explainer of the response variable. 0 for R squared would mean that the predictor is a very poor explainer and doesn't explain anything about the response variation. Here's a picture of the parts of the variation. Here is the representation for the variation in the points around the average of y. In other words, when there are no predictors in a regression model, the variation in the points around this y value or y bar is SYY, the total variation. We saw that right here in this formula. And the sum of squares regression is basically how much of the variation in the y values around their average can be explained by this straight line. And so it's the part left over between the variation around the line, the regression line, and the variation around y bar. And so the larger or the closer that the points vary around the sloped regression line, the bigger this part is. Well, we could look at it this way. It'll be smaller residual sums of squares, making this nearly 0, and r squared would be very close to 1 if the data values were very tightly packed around the summary least squares line. You would mean the residual sums of squares would be quite small in that case, making r squared big. If the data points were just sort of randomly scattered around the overall average of y with no trend, r squared would be very small and there would not be a strong pattern. Finally, we're going to use residuals to try to understand whether our simple linear regression model is any good or not. And we do that through a residual plot. Residuals will be on the vertical axis, and either the value of x or the estimated values of y will be on the horizontal axis. As the second bullet points out, the ideal residual plot should have just a random scatter of points, residuals around a value of 0, and it shouldn't have any notable upward or downward spread. Here is a very good looking residual plot for our old faithful model. I have the residuals here on the vertical axis, and a value of 0 would mean a point where the actual waiting time for the eruption was exactly what we would have estimated from the least squares line. You notice there's a few eruptions that almost fit that perfectly. And a value like 15 would mean that we had to wait 15 minutes longer than we were expecting. A value like negative 10 would mean that the next eruption had occurred 10 minutes sooner than we were expecting. The number of minutes that we were expecting are these predicted values. These are the y hats. This is a nice looking residual plot because the residuals are sort of evenly spread right around 0. There's no notable upward or downward trends or patterns in this residual plot, suggesting that the simple linear regression model is a reasonable explanation for the scatter plot that we've been looking at in this data example. Let me know if you have questions.